Hopkinson bar data analysis tool. You have two options. You can run it from MATLAB as M files, or you can grab it as an executable from Mississippi State's ICME website, which is located here. You can download the MATLAB files from the MathWorks file exchange. You simply just Google split Hopkinson pressure bar MATLAB, and it should be the first hit there. So assume that it's downloaded in the correct spot. If you're using the executable, you'll need to also download a runtime engine for MATLAB. And if you download the open source versions, you will get 4 files plus some example files. The 4 files you will get are a figure and an M file. That's the force displacement to stress strain file, and that's the GUI, and then that's the calculations behind the GUI, and then here's the analysis portion. So to begin with, we can run the portion which takes a voltage and then outputs a force displacement. This tool can handle various types of data. You can import your voltage files from an Excel file as long as it's formatted as 2 columns. There's an option. You can also just import the voltage files as, so say this is our incident voltage, and then there it asks again for a transmitted voltage, brings those in and populates this data. The incident wave file and the transmitted wave file will populate some titles to make sure you haven't clicked on the wrong files. You have options to flip the incident or transmitted voltage if in the experiment it used the wrong sign. You have the sampling frequency that you need to provide, and then in the strain gauge for the incident and transmitted bar, you need to provide the strain to voltage factor. You also have the option to provide the distance of the sample. However, this value will change interactively as you begin to align the beginnings of each wave. Then the mechanical properties of the incident and transmitted bar, you have the wave speed, the diameter, and the density, which will be used in calculating the velocities and the forces. Then you also have the option to use dispersion from some predefined Poisson's ratio, or you can use your manual values. There's 3 figures on top. One's the raw data, just as it is. No change will ever happen to this plot. Then you have 2 plots to the right, which show as your data is, the offset is nulled and the waves are clipped, you will see these figures will update. So in your offset nulling, there's a algorithm at the beginning which attempts to find when the test actually begins. And so here in this case it did relatively well. There's this, what it considers the 0 signal, and then it kicks up just a little bit. We're assuming that's where it begins, but if we want to check that, you can hit these sliders. There's 2 sliders for the left side if you want to bring your data from the left inwards, or you can bring the slide from the right inwards. If you click the arrows, it goes by 1 data point. If you click inside the slider, it'll jump 10 points. So it just jumped 10, and that looks relatively close to what I think a 0 nulled wave is. Then for the transmitted bar, it looks like it got it already right, but I can jump ahead 10 and know the data. You can see that's where the wave starts, so we can jump back 10 and say that's a good 0 average. So what it will do is average all these points inside the window, the offset nulling window, and it will shift the raw data up or down accordingly. The next 3 groups of plots is where you can shift the waves to line up. And again, this could be changed here by changing this value, or you can manually interactively move waves to make them line up. And so these 2 plots are actually the same, with the change of this value here enables you to look at in greater zoom at the beginning of the wave, or in this area, so you can look closely. So already we're pretty close with the incident and transmitted wave. However, for the reflected wave, it's way off, so we need to shift that over considerably to line up. So as you see, I'm clicking, it is moving here. You can watch that until it lines up appropriately. And then finally, you have another slider down here that shows the length of the wave. Again, there's some algorithms in here that do their best at guessing this, so you don't have to click as much. It may get it sometimes. If it's a pretty noisy test, it may not get it, so you may have to just do it yourself. All right, finally, now that we've shifted and nulled the waves, you can enable the calculated plots. You can enable these things all along as you're shifting, but what happens is there's going to be 4 plots which have to populate with some calculations behind them every time, and so it just slows everything down a bit within MATLAB. So yeah, you can keep this enabled as you shift, but it takes a second to update every time. What we're seeing here, you have 4 plots: force time, velocity time, displacement time, and then force displacement. In the end, you're going to be sending out force displacement, but the rest of the 3 plots are helpful to see whether or not you like the test as it stands, because the incident end and the transmitted end, the general curves ought to line up closely. The incident end is going to be much more noisy due to just the stress not being at equilibrium there, but the transmitted end will be much smoother. And then same with the velocity. We would hope that the velocity at 2 different ways to analyze that: the incident minus the reflected wave versus just the transmitted wave. You can see the general trend is identical, so that looks like it was a really good test. And then displacement data is pulled from the velocity. And then finally, the force displacement, there's 3 to 2 to 1 wave analysis that you can use. Most people use 1 wave, looking through literature. You can pull up the journal article that walks through the theory behind this GUI and kind of dig in to see what the difference between those things are. At this point, we can move from this portion of the data analysis into the manipulation from force displacement into stress strain data. So you can output a restart file, which would recommend that, which will save all of the data which you see here, anything in the boxes, the slider locations, the wave files. You can save strictly the force displacement, but if you don't want to do a stress strain analysis, and then you can also jump straight into the stress strain. I'll take these curves and go into the stress strain analysis. So let's go ahead and do that. What we'll go ahead and do, though, because it's commonly easy to forget to save your work, it will go ahead and save a restart file with the time, a timestamp, and the file name. So SS, because that was the name of the file, and then a timestamp. Okay, it asks, do we want to use the 1, 2, or 3 wave force displacement curve? We'll use the 1 wave and export the data, which brings us to a second window. You can jump straight to here if you already have your force displacement data, and you can run it from this MATLAB file here. Here we have the file name is saved from the previous window. You can change the sampling rate, the length, the diameter, or the area. The diameter and the area are they interact with one another. If you change the diameter to 5, it will update your area. So if you have a whatever measurement you've taken, these two will interact. Next, you have a modulus correction, which I'll explain in just a minute, and you can tell if it's a tension or compression test. So what the modulus correction, what it enables you to do is to clean up the elastic portion, this area of the stress strain curve, since it's generally accepted that the elastic region is not helpful in the high strain rate test due to a nonlinear stress wave hitting that area. What will commonly happen during tests is that this area will have little toes in the data, or just use an example here. You can see how it curves over, which physically doesn't make a lot of sense. So what this tool enables you to do is to clean up this area, since we won't use it for any modeling anyway, for any future work this could get passed on to. You have two sliders here, which attempts to bracket the most linear portion of the elastic region. So the left slider pulls in from the left side, the right slider will add or delete points from the right side. So as I move this slider, it moves the amount of data that it will try to fit a line to, and that line is the slope, the modulus. And since I haven't really given it a realistic length of diameter, the modulus could be off, but now it provides you, if you do want to know what your modulus is, it will give you that. If you want to correct it anyway, you can do that there, or at this point I will just copy the modulus that it calculated. At this point, what you could see is these two are identical. The moduluses are identical, and so what happens is it gives a much cleaner elastic region. But user beware, this can, if not used properly at large strains, if there's a big difference between the observed and the corrected moduluses, it will, and strains large, and this is only going to 13%, but if strains much greater than that, 50% or greater, we'll find some very unrealistic trends in the stress strain behavior. So there are times when this should not be used. Finally, there is a plot down in the bottom right to show the strain rate. You have the option of changing the x-axis there from time to strains to true strain engineering strain. In any of this data, so your stress strain, your strain rate, true strain data, can all be exported. Everything can be exported, or you can pick particular curves and export them.